Hello everyone. Uh, in today's class, we do a typical machine learning experiment. Basically, we start from scratch, reading a file, doing data preparation, then feature selection, prediction, and then analyzing the results. So as you see, this is my database. It has 19 independent columns. This is stuff from column 0 to column 18. And the 20th column is my dependent variable. So as you see, there is some empty cells, which is pretty typical in machine learning projects. And also, my dependent variable also has some empty cells. On top of that, although column 12 has numerical values, but these are levels. Let's say that like a star rating is either 1, 2, 3, 4. So the thing that this is also a categorical variable. It's not a numerical. Although the levels identify with 1, 2, 3, 4, 5, but there doesn't mean they are integers that represent a numerical variable. Instead of 1, 2, 3, 4, 5, they could be A, B, C, D, E, F. But it just shows 1, 2, 5. So again, column 12, column 7, and column 4, all of them are string or categorical variables. I have empty cells everywhere. So what can we do first? First, check if NIME understand their real, if NIME could understand the actual variable type. Let's say if NIME can understand if they are numerical, categorical, and so on and so forth. For me, column 4, column 7, column 12, and column 19 should be considered as string or categorical variables, and the remaining should be numerical. Then I should take care of empty cells. As you see, column 4, 6, 7, in those columns, most of the columns are full. I have just few empty cells. So imputation makes sense, even column 13. As you see, most of the column is full. There is just some empty here and there. So imputation there makes sense. But look at column 10. Most of this column is empty. There's just few values. You still can do imputation, but since almost a high percentage is empty, you can just get rid of it. However, just keep in mind, it's an important subject. You cannot do imputation on your dependent variable, which is column 19 here. We never do that. So whenever we see empty cells or observation in dependent variable, we just drop the associated row. It's the way that we do predictive analytics. We don't impute and predict. We just drop those observations. Having been said, I made a typical NIME workflow for doing a machine learning project. In each step, I show you how to deal with this data set. You can add extra steps for your project. For example, you can check if you have some outliers and get rid of them, or treat them in a way that makes sense, or you can just do observations and check if the values in your table make sense or not. Or you can do some figures. Even you can use a Tableau for doing that. So anyway, this is a typical workflow. Let me show it to you. This is a typical workflow. Again, you can add extra steps. For example, outliers, making visualization, so on and so forth. But it gives you a good structure, what you should do from beginning to the end. And you can just add on top of this structure. So first of all, you might be a busy workflow, which it is. There is some ways that you can organize this workflow. For example, just changing the locations. Or you can make a meta node or some other thing. So let me just show it to you. I select this node, this node, this node, this node. Right click. I can make either component. Let me show you how a component works. You can just leave it any name here. Now it's much more organized now. But if I click, I cannot see what is inside the component. It's very hard to edit it. So let me just get it back to the previous composition. So again, I do right click, go to component and expand. Another way of dealing that is make a meta node. Again, I select these 4 nodes, right click, create meta node. You can leave any name. Voila. So again, they organize in one node. If I click on it, now I can see what is inside the node. I change the location, double click on each node and just play with that, edit what is inside the node. Let me close it. And just, I go to meta node and again expand to the previous composition. Okay, let's do one by one. First I go to Excel Reader because I want to import Excel file into 9. Double click. First, you need to browse and find the file. Click on it. I put the file and this workflow over models, so you can see that. I said table contains column names in the row. We know that the first row for is column names. I think the remaining you can leave at default. Also, you can refresh here, see if it looks good. If you see any anomalies here, you can again play with these parameters. Press OK. Name to a string. Oh, so let me just see what we imported. So when you do right click and go to output table, go to second tab. As you see, column 4 is a string, is good. Column 7 is a string, good. Column 19, dependent variable string, good. But column 12, it had some numerical values there, but we know that this variable is a string, it's not a numerical column. So we need to convert it to the equivalent, we need to convert it to a string, same as 9, 7, or 4. What can we do? We can do it with number to string module. Let me double click. As you see, in the inclusion part, let me just first it's like this. I know that I need to convert column 12. I select, move it to the right side, then OK. So it would convert it to a numerical value. So let me reset first. Reset. Then I go to this one, execute. Let me right click. Now I go to transform input, second column. Now column 12 is string, so good to know. Then missing value column filter. I already told you that column 10 had too many missing values. Again, it doesn't bother if you impute, but it's also good to just get rid of it. Let me show you this module. I just said include all of the columns. So it's first like this, then I click in the second arrow to put all of them in the right side. Then I'm just saying that the threshold is 90%. I think the default is 10%, but I changed it to 90. So if a column with 90% empty cells, if we have that, we should get rid of it. So it's what this module does. Okay, let me right click, execute, then right click, filter table. There is no column 10 because I told Naim that whenever you see 90% empty, just get rid of the column. So, but the remaining are there. So I just got rid of column 10. So, but now we should play with our missing values. So what can we do? First of all, we know that we have a dependent variable that we shouldn't do any imputation. We just should get rid of those empty rows in the dependent variable. But for independent variables, if they are numerical, we can impute with mean, median, or other approaches. If they are categorical or string, we can impute with most frequent, which is mode in the statistical term. So having said that, look at the missing value module. Here I just said if it's numerical, impute with median. If it's a string or categorical, impute with most frequent value or mode. Or you can select next value, fixed value, do nothing, or remove, which we don't want to do that. However, go to the column settings. Let me just remove it. So I know column 19 is my dependent variable. I click on it. And I'm just saying that remove row. So whenever there is a empty cells in column 19, which is my dependent variable or the variable that we want to predict, just remove that variable. We get a warning, that's fine, but also here we define, in the missing value module, we define the regulations. Then we need to apply. So again, as you see from previous module, there is two output. One is going to missing value definitions or regulations or settings. And the second one go to the missing value apply. So in missing value module, we define what we want to do with those missing values. And in the missing value apply, we apply those filters or considerations or imputations. So, but if there isn't one input, it coming from the previous data, one input comes from regulations. So I right click here and execute. Okay, let's open it again. So on missing value apply module, I do right click. As you see, there is no empty cells. Okay, look at column 4, column 7, and even column 12. These are not numerical value. These are labels or strings. Vast majority of algorithm machine learning domain cannot work with those variables. What I mean, their input should be just numerical, same as other columns. Although again column 12 looks numerical because numerical labels, but actually is a string, like a star rating for Amazon, or when you go a hotel, every hotel has ratings. So these are labels. So what should we do? We should encode these columns to equivalent numerical values. There is two ways of encoding. Encoding again means convert a categorical or string column to equivalent numerical column or columns. One way is label encoding. Label encoding just converts them to the numerical value just to one column. For example, instead of ABCD, it would be 1, 2, 3, 4, and it assumes now it's just their numerical values. FGH, it could be 1, 2, 3. Column 12 would not be changed. Still, it will be 1, 2, 3, 4, 5. But machine learning algorithm or other modules deal with them as a numerical values. So one way, again, instead of ABCD, we put 1, 2, 3, 4. Instead of FGH, maybe, or 10, 11, 12, any numerical equivalent. Another approach is hard encoding. I talk about hard encoding later in the class, but just for now, you can just Google it. Let me show you. Because again, it's related to statistics, not your class topics. So just Google hard encoding. Oh, even bring it. So there's Wikipedia or other pages that you can get good ideas what does hard encoding. Another one is label encoding. The most common term, instead of, they usually say one-hot encoding, not hot, but so either one-hot encoding or label encoding. So please do your research. Again, you are graduate students. You should be able to do independent researches. But anyway, for today, we do one-hot encoding. What does it mean? We convert one categorical column to several dummy variable columns that are equivalent to that column. But no worries, I show it to you. So look at one-to-many. I just do it for independent variables. So I select column 12, 7, and 4 because the type is a string. I include here. Again, right click, execute, right click, process a table. So look at here, I have column 7, column 4, and column 12. But look at this one. Now I have extra column A, B, C, D, E, F, G, H, F, G, H, 1, 2, 3, 4, 5. Let me check again. Oh, I shouldn't include 19, sorry. So let me Oops. Execute. Look at the first row is A, is not B, C, D, or others. Okay, let me go to show it to you. Now I have A, B, C, D. A is 1, B is 0, D is 0, C is 0. But what does it mean? First observation was A. Look at here. Second observation is D. What does it mean? If I have now 4 equivalent columns, D should be 1, the remaining 0. Second observation, as you see, D is 1, the remaining is 0. And let's just check one more. Observation, the next observation is C. And so the C column should be 1 and the remaining 0. Let's go there. Yes, C column is 1 and the remaining are 0. And same for FGH and 1, 2, 3, 4, 5. I hope you get the idea how one-to-many works. Now I do partitioning. So in partitioning, I divide my data in 2 sections. One for train and test, another one as a holdout set. So train and test, you can, in the train and test section, you can do 5-fold cross-validation or just one train, one test. Holdout means a data set in the future that you apply your model on it. Here, all of the data is given, so we just randomly divided in these sections. But in real case, you have a holdout that comes in future. You don't have any idea what would be the prediction, so you apply your model for prediction. So anyway, for now, let me just open it for you. I'm just saying do relative 80% division, means the first data set, which is for train and test, is 80%, the remaining is 20%. 20% is suppose the data set that we don't have any idea and comes in future. The remaining, the 20% is the holdout that comes in future when we don't have any idea, and the remaining 80%, we can do 5-fold cross-validation or just one train, one test. I'm just saying stratified on column 19. Column 19 was my dependent variable. It has 4 categories. When I do division, although the division happens randomly, but what happens in my train set, I want to have instance of all categories. I don't want to have my dependent variable just have category 1 and 2 and not having 3 and 4. What does it happen if my train set just have 1 and 2? I train my model on just these 2 categories, and it wouldn't learn enough to do prediction for category 3 and 4. It could bring some error or bias. So do you remember that in the previous class I talked about bias in prediction? One could be you don't have a good train set that doesn't have enough observation from each category. In that case, we had female and male observations. Here we have bus, van, Opel, or different categories. So when I say stratified sampling, it means I want to have samples from each category. So my algorithm would be learned well in all types of prediction. There is another section which is random seed. So your data is divided randomly, for sure, but we want to just keep it for future re-evaluation. So what does it mean? So if in the random seed, I put 1, 1, 0, what does it mean? Next time that I open 9 and run it again, I get exact same result. So every time I get same result. I can deselect it, but next time that I run the 9, my result would be slightly different. is actually fine. But let's say you want to write a report to your whatever, to your boss in the industry, or you want to publish a paper. And let's say today your boss asks you what is the probability of increasing the stock market, and you said 81%. And 2 hours later, he asks you to run it again, and again this time you get 80.8%. 80.8% and 81%, almost very similar, but there's a slight changes. So you don't want to have those slight changes. So by selecting random seed, every time you get exact same result, and that's fine, but it's not necessary, but you just want to have a stable results every time. You don't want to see even very slight changes. So I press OK, run it. Oh, sorry. Right click, execute. Again, I want to make less messy. So far what we did, we take care of the column type, we take care of missing values, and we partition our data in 2 sections. One section for train and test, another section for the holdout. And as again, in the reality, holdout comes in future, you don't have any idea, but this is just for evaluating our model. In many cases, train and test is enough. So in some, if you look at some technical paper, they just have train and test, they don't have holdout, that's fine. This is just for extra evaluation. So I select these 4. Maybe all of them. Right click, create meta node. Oh, it just said it would be the reset. Yes, okay, let me see if I can include this 4. Hopefully this time it should be fine. Execute nodes will be reset. No. Let's see what happens this time. So right click, create meta node. Yes. Instead of meta node here, I put data preparation. Okay. No worries, I have a random seed, so I execute. Okay. I just put it here so it is less messy. Let me delete the name. Okay, so I have another meta node here. And so just let's forget the 20% that goes to the holdout set, and just focus on our train set. So train and test set. I have a meta node of feature selection. I've taught you when we have too many variables, sometimes if you use all of them in prediction, you may overfit your model on the train set, and it wouldn't get good result in the test set. So one of the ways to avoid that, doing feature selection. So we use another algorithm to look at the variables and select the ones that are more relevant. So instead of focusing on too many variables, we have a small amount of variables. So in that case, is one of the ways that we avoid overfitting, but it doesn't guarantee. So you just do it by try and error. So to my try and test part, which is 80%, gets 2 copies, and both of them go to this feature selection meta node. And again, one section goes to the holdout section. So let me click on meta node. So the upper part is more complex. As you see, I created a loop which start from this blue node up to this. So as you see, this is the general structure of feature selection. Basically, in feature selection, we use a predictive algorithm, and then we just see how many variables brings a better predictive performance. For example, first it picked the first variable, then just add one more variable, add one more, until it gets to the point that highest accuracy achieves. And just record all of those variables and use it for future. So what it does, you need to have two of the feature selection start loop and feature selection end loop. Within that loop, we partition our data in train and test. As I said, it's similar to prediction. So here I use naive-based learner for learning and predictive. You can just replace the model. Maybe at the end of the project, your accuracy is low, or ROC or other measures, you want to improve the performance. So maybe instead of naive-based learner, you use SVM or random forest or other algorithms. So in partitioning, I partitioned the data into 70% for train and 25% for test. And again, is an arbitrary number. It's better to be something between 70 to 85%. Again, random seed, I put, let's say put, again, another number, 111, 110. So then I do prediction. In the scorer, I just generally can look at the performance of feature selection, the predictive algorithm that I use in feature selection. And in here, in the end loop, it just show you how many variables brings which performance. So let me just go to the end of the loop, right click and execute. Okay. So right click, you can look at the performance of the feature selection algorithm. You might say, Hamid, the accuracy is just 82%, but you know, my dependent variable has 4 categories: van, bus, sub, and opal. So if randomly, if you don't do any predictive algorithm and choose by chance, the accuracy should be 120 divided by 4 equal 25%. So the random selection is just 25%, is 42. Maybe you can use better algorithm and improve the accuracy, but 42 sounds scary, but it's not too bad here. Much better than 25%. And here, by the way, this is the last predictive performance. Let me show you here what I mean the last. Let me go to the result. So as you see, first it shows column 11 as my independent variable. The performance was 41. Then column 18, 49. It just is a forward selection. Again, forward selection means first you pick the best variable and then add one by one. As you see, when it adds more variables, it's almost increasing up to this point, 59. Then by adding column 0, it just dropped the performance. Column 4, a little improvement. up to the last one. You see, so this is what you saw here is the last performance, which sounds scary, not too bad, but it doesn't mean it's the best predictive performance. So what you saw here, 42.8, it just means what happens to, let me just expand it here. What happens if you have all of the features? So if you see, if you don't do any feature selection, the performance would be 42%, 42.8%. But if you have lower number of variables, we have a better predictive performance. So now let me run the filter, open it. I just said the threshold is 0.5%. And this is the amount of variable that it picked for me. So if I right click, column 19, okay, again, filter selection filter, we just filter out how many, which amount of prediction accuracy we want. So what I mean, let's say my threshold, let me just put my threshold 0.6 or 0.7. Look at the predictions. There is no prediction with 0.7. So the output would be crazy. So let me just, okay, run, then right click, filter table. Nothing is selected, you know, because in my feature selection predictions, there is no 0.7 prediction. All of them are less than that. So this is the range of predictions from 0.416 up to 0.596. If I say my threshold is 0.584 or 0.58, so all of them would be chosen. So 10 variables, 0.584, 12 variables, 5.84, up to 8 variables, 0.596. Let's say I say my threshold is 0.59. So 0.59 or 5, let's just make something easier, 588. So these last three are more than 588. And but it doesn't give you the maximum. It just gives you the one that satisfy your threshold and has lowest amount of variables. It means okay, execute and see that. Let's see how many variables I have. 1, 2, 9 is not included because 19 is my dependent variable. 1, 2, 3, 4, 5, 6, 7, 8. Plus 19 would be 9. If you look at here in the configuration, this is the lowest amount of variable is 8 variables and also satisfy my threshold. So when you put the threshold, it just try to find the minimum amount of variables that satisfy your threshold. With 8 variables, you are more than 588. With 9 and 11 also you are. But the point that in feature selection, we try to find the lowest number of variables that could bring a good prediction. So it's the reason the lowest amount of variables more than your threshold is selected. Let me execute, close this section, which is a meta node. So I know now which variables I have. So the last part is feature selection. sorry, prediction. So again, I have a partitioning. So I need to divide my data into two sections of train and test, which is much easier. Here, I want to do 5-fold cross-validation. Basically, I want to see if prediction on each fold is stable. Let's say in one fold, my prediction is 0.6, another 1.4, another 1.8. There's a huge variance, which is not good. It just means your model is not stable. So what I do here, I do 5-fold cross-validation. As you see, I have here in partition, I just said I have 5-fold cross-validation. Class column is 19, which is the dependent variable on random seed. Let's again put 110. So one section goes to SVM learner. So here for predictive part, I want to use SVM. You can use other models. Another one goes to predictor. So look at this triangle of partitioner, learner, and predictor. Is how you do 5-fold cross-validation. So I come to the later point and right-click and execute. Okay, now I did 5-fold cross-validation. I can look at the performance and also use it for future. So far I did a lot of things. I did data preparation, feature selection, training with SVM learner. With PMM writer, you can use all of these steps for future prediction anytime. So in this model, in this module, you browse to the location that you want to save your model for future prediction. You can even select override. So, okay, right click, execute. So now I'm using this preparation, feature selection and prediction for future use in here. Also, another output of SVM learner goes for holdout set. As you might remember, the first partitioning, we select a portion of our data as a holdout. So after doing 5-fold cross-validation, again means you divide your data in 5 folds, use 4 of them for training, 1 for test, and next time you use another 4 for test and remaining 4 for train, and you just repeat 5 times because I have 5-fold cross-validation. The outcome comes to check your holdout set, but we just keep it for now. Now I want to see what was the performance of my 5-fold cross-validation. What happened? Is it a good model or not? If it's not, I can just play with my SVM learner to choose another training algorithm. Also, maybe I can change my feature selection algorithm. Here was naive Bayes. And also in data preparation, I can impute with other approaches. So for example, instead of using median for numerical imputation, I can use mean or other approaches. So from now, I want to check the performance of 5-fold cross-validation. I want to see what happened. Is it a good one or it's not? Okay, now if we want to loop through the folds, since we have folds 1 to 5, we should do a loop again, similar to prediction part, and then look at the performance of each loop. Also see if there's a huge variance between each loop or not. If there's a stable and high variation, a stable variation and high accuracy, it's good. And again, I'm talking about accuracy as just a sample of performance measure. You can check ROC, sensitivity, specificity, and other types of performance measure. So here, after predictor part, we make a X aggregated module, start group loop start for each fold. A scorer gives you performance of each fold, and end loop. I also have a scorer to give us the aggregated predicted performance of the loop. So in the aggregated X aggregator, I identify target column, which is my dependent variable, and what I predicted. That's one. In the start loop, I identify the fold, the column that associated to the folds. Okay. A scorer gives you the predicted performance of the last fold. So if you know we have 5 folds, so again here I should specify my dependent variable, column 19, and what I predicted previously. And in end loop, I think you can just leave it as default. Okay, let me come here, right click and execute. So again, in Scorer, you can see the performance of last loop, which is fine, but we want to look at what happened in each loop. So in each loop, for each category, you can find true positive rate, false positive. Again, you can drag each column to the right to make it wider to see what is in there. True negative rate up to the overall accuracy. So 57.9, 549, 617, 602, and 561. Frankly speaking, predicted per accuracy, the overall is not too bad, but there's a high variation. Maybe we can play with the better feature selection algorithm, better imputation, or better predictive algorithm, or trainer or learner here. But this is just an example. Again, here I just use one feature selection algorithm. You can add more feature selection algorithm, for example, SVM, neural network, or you can just Google for feature selection algorithm. You can either do union of all features or intersection. And maybe you come up with better feature selection outcome. On top of that, you might remember we had one-to-many for one hot encoding. Maybe you can do label encoding and get better results. So there's a lot of things that you can play with that. Even for SVM learner, you can play with this parameters of SVM, better performance. So what I see from your final project, you should add to this structure, not just give me something similar, just changing the input variable inputs for your project. You need to show me that you did some try and error. Maybe you changed the learners, you changed the feature selection. Maybe you use 2 or 3 feature selection algorithm. Maybe you try first one hot encoding, then label encoding. So I need to see some, at least 2 or 3 efforts from you to improve. First of all, here, you had a better accuracy and also stable performance. As you see, here is 58, 55, almost 62, 60, 56. It's a high variance. This is not a stable model. So maybe we can just run this one. Look at the overall prediction. And in group by is another way to show the average of or mean of predictions and also variance. Let me double click. In here in the manual aggregation, Let me remove all. I want to look at accuracy mean. Oops. Another accuracy, and this time maybe variance or a standard deviation. I think a standard deviation is better because it would be in this same dimension of your actual data. So standard deviation. Maybe one more. Let's look at sensitivity. Mean and standard deviation. Specificity. Mean and standard deviation. Then press OK. Run. Then right click, see the performance. So as you see, the mean of accuracy is 58.1, which is similar to what we saw here in a scorer. Sensitivity 58 with 0.23 variance is a huge variance. Specificity is 86, 0.04 variance. As you see, your specificity is much more than sensitivity. It's not really good. And actually, the standard deviation of your accuracy is not too bad, but you can even improve it. Or instead of having the mean of 58, maybe you can have 65 or 70. So again, with PMM Writer, we save it somewhere on hard drive and use it in future prediction. So you might remember the early part of this model. We divided our data in the hold out, train, and test. A portion of data, which let me open it, 20%, because 80% was for train and test, was for holdout. We did the learning here. We use the outcome of the learning here, the input as the 20%. We do prediction. Okay. So right click, it's already executed. So then with the scorer module, we can look at the performance of our prediction. So let me look at. So now performance prediction is 53. Again, I had 4 categories. The random, if by random selection, the performance would be 25%, 53 is almost twice 25. But there is some rooms for improvement. Again, we want to have improvement for your final project or other projects. Especially for your final ones, if you do predictive analytics, I expect you to try 2 or 3 ways to improve their performance. ROC, sensitivity, specificity. What I mean, for example, you play with the encoding part. Here, I just use one-to-many, one-hot encoding. Maybe you try label encoding. For feature selection, maybe I use one. Maybe you can use others. Try to improve your feature selection using other algorithm, or add 2 or 3. Let's say you use naive Bayes, you use lasso, you use neural network. You either do union or intersection of those features. What I mean intersection, let's say you use SVM, it gives you 10 variables. You use naive Bayes, gives you 8 variables. And use lasso, it gives you 6 variables. 6, 8, 10. But 5 variables are same in all of them, so use intersection of them, which is the common between all of them. Or if you do union, 5, 6, 8, and 10, maybe the union of them would be 12. I use that 12 for prediction. So you need to play with that. There there is some approaches to maximize it, but it's out of content for this class. You just do by try and error. So for example, for SVM learner, you can use neural network. Maybe you get a better performance, or random forest. Again, there is certain ways that you can try, and your final project, if you do predictive analytics, I expect you try 2 or 3 of them and improve your prediction. Again, for a scorer, I just use accuracy, but you can use auto. I also want you guys to do ROC, sensitivity, specificity, accuracy, at least these 4. And but here I just show you how to do accuracy. In the other classes, I show you how to ROC. You can just Google it, it's not difficult. Anyway, this is the basic structure for your final project. You shouldn't do just this and without any changes. Also, I just forget to say, in one of your classes, I talked about outliers, how to take care of outliers. So maybe you do it here too. Maybe there's some outliers that ruined your prediction. You take care of them. Or some of the values doesn't make sense. Maybe you need to exclude them. For example, let's say you want to predict somebody's blood pressure, and the weight is like 2 pounds or 2,000 pounds. So these are the value doesn't make sense. You can take care of it by outlier, or just, even they are not outliers, might be in some cases. So you need to do descriptive statistics beginning, look at all of the columns to see if the variables make sense or not. If it doesn't make sense, take them out. And it's another way to improve your performance. Anyway, that's for today. Please start working on your next assignment and also your project. For your next assignment, I don't expect you to try different approaches, maybe, but don't just use this structure for your next assignment. In your next assignment, just change some part. For example, instead of SVM, use another model, or instead of naive Bayes for feature selection, use another one. But you can use this structure for your next assignment. But my expectation for your final project is much more advanced, and also you need to do some search and to improve your performance. Thank you very much, and have a great day.